Good afternoon. It is my great pleasure to introduce the next speaker, Dr. Alberto Nandani. He obtains his PhD in chemical science from University of Milan, Italy, in 2010. From 2010 to 2017, he worked first as postdoctoral fellow and then as research science at the Italian National Research Council in Milan. Since 2014, he is visiting scientist in the nanophotonics group of the BRIC Nanotechnology Center in Purdue, USA. Recently joined the Regional Center of Advanced Technologies and Materials in Czech Republic. As co-leader of the Photoelectrochemistry Fuel Cells Division. He co-authored 37 papers in peer-reviewed journals, has been awarded with 4 research grants and 12 funds proposals that worth the access to international research infrastructure. His research interests focus on the nanomaterials for energy and environment with a special emphasis on photocatalysis, plasmon-enhanced chemical transformations, electrocatalysis defects, and doping in metal oxides, charge transfer, and solid and solid-liquid interfaces. So let's welcome the next speaker with applause.
And to change the presentation slide. Okay, thank you for Cesar for the kind introduction, and also I would like to thank Jose Galvis and all the organizing committee to inviting me here, giving me the opportunity to give lectures in the school and also to present my research of the last years about plasmonics. And in particular, today I'm going to talk about how we use plasmonics to develop new technologies for clean fuels and solar thermal devices using heat generation. So indeed, maybe I will give a different perspective on surface plasma if we see what has been presented so far in the school. And I will talk more about the dissipation of surface plasma. So hot electrons generations and heat generation for developing new technologies. So I just wanted to take large. And so, as you know, we are really facing an energy transition which is really driven by the needs of providing more sustainable energy economy for our planet. Indeed, in the last 50 years, we have been facing the depletion of fossil fuels and also the increasing of pollution and depletion of natural resources. This is of course, a problem which touches every country from the more developed to the underdeveloped country. And therefore, we can see that after really, I would say, 20 years of increased public concern, in 2015, there was the Paris Agreement where policymakers decided that we have to stop this tendency, and basically the target is to limit the climate change, so the rising of temperature by 2 degrees, more or less. And this, of course, is really a challenging task, and as we can see, this means that we have to deplete to provide basically reducing 70% the CO2 emission, and which means by the 2050. And therefore, this calls for the deployment of massive renewable energy devices and technologies. So I would say that I would want to report this to remark that the policy is really the starting point to make this change happen. And this is really a nice example which was being reported in Natural Energy last year which show the Germany energy transition. Here, Germany really in the last 30 years, I would say, really start a renewable, sustainable policy. We can see that they decrease the use of coal, of nuclear energy, while increasing steadily the use of renewables, from bioorganisms, from PV, and so on and so forth. And so we can see different example in Europe, for instance, which is where I live. Denmark has a 63% of renewable energy share in its pie, and Germany 27%, while Spain also is really working well with 25% of renewable energy. So here renewable energy is really taking into account all the type of renewable energy, which means hydro, wind, bioorganisms, and so on and so forth, PV, etc. So I'm, of course, more interested in many different technology, and here we can see a picture of how the technology will develop probably in the next 20 years. Maybe here. So, sorry. To produce clean fuels and really increase the sustainable energy economy, to produce a circular economy, I would say. So we will probably use small molecules like nitrogen, carbon dioxide, and water to produce clean fuels such as hydrogen through electrocatalysis, photoelectrochemistry, or photocatalysis. So we will use the sun to store the energy of the sun into the form of chemical bonds and use these on demand. So we will just, we will therefore overcome the problem of intermittency of the sun. Of course, there will be great exploitation of wind and hydro technology, as well as also PV technology that will power, for example, device which will use electrocatalytic technology or photoelectrochemistry to have these clean fuels. And this is really it's not just science pictures in the magazine, but this is really something which is really going on. And so far, for example, there are big funding which are given in China, in the US, to develop this technology, but also Europe has fostered the creation of two flagship initiatives about solar fuels, which means that this project will have €1 billion in the next 10 years to open calls about renewable energy. And this is not just fundamental research, but they will really push to have advanced TRLs for solar fuels, which means already producing devices that can be used on a large scale. And the target is to produce like terawatt of kilowatt-hour, terawatt energy for Europe by 20 years. And one of the technology that is not present here is solar thermal technology, which I think is really interesting because and is really developed, I would say, except for a few cases. So we can think that we spend 50% of our energy that we produce to heating and cooling, and only 10% of this energy to produce heat or cooling is renewable. And of this 10%, only 7% is produced by solar technology. So which means that there is really a big opportunity to use solar, to develop new solar technology for solar thermal devices. And this, of course, can be used in really different places on Earth. And for example, here I just give a glimpse of what we can use, what processes are driven by heat in our societies, so catalysis to produce chemicals, polymers, pharmaceuticals, or to produce distillation, so to purify liquids for heating and cooling, steam generations, which means, of course, producing electricity with turbines, or for space heating. So really many different opportunities here. And here I would start with this simple slide, which is what we do. So we use surface plasmons, so this surface surface electronic wave density oscillation at the interface between conducting materials and dielectrics to develop this idea of new technology for renewable fuels. And in particular, so we can use, of course, the main points of surface plasma is the concentration of light at the nanoscale, as really well outlined in the classes of I saw yesterday. And of course, but we can use what's happened after we concentrate light at the nanoscale. So this big amount of energy is dissipated, and so we can use the hot carriers, which are generated from the dissipation of the plasmons, to do something useful. So for instance, for catalysis, so driving chemical reaction in an efficient way. And after that, these carriers dissipate, producing a really large amount of heat at the nanoscale. So we produce local heating, which can be used for many things. For instance, so we can produce devices which have really high temperature generation just using light and heating the part that we are interested in. And this is very important because if we think to thermal process, we really have to put a huge amount of energy to use high temperatures processes. And so today I'm going to be talking about alternative plasmonic materials, in particular refractory plasmonic, so using metal nitrides as plasmonic materials. These materials and I will talk about the optical properties and mechanical properties of these materials. And also I will talk how we can use these materials in to enhance the photocatalytic hydrogen production for water splitting. And here is interesting, hydrogen is not just really some kind of fancy idea, but is really something real. So in Germany, again, 5 months ago has been started the first 2 lines of train, which are fueled by hydrogen with fuel cells. And so this is something that's happening right now. And finally, I'm going to talk about solar thermal technology, so our really efforts of the last 3 years to produce new plasmonic materials, which really heats up a lot and can be used for many applications, from solar thermovoltaics to steam generation. So let's start with just a glimpse of alternative plasmonic materials. As you know, maybe something about plasmonic, and you see that most of the time the materials which are used for studying this technology are gold and silver. Of course, we know very well the optical properties of these materials. But the problem with these materials, for instance, is that they are not very chemically stable or not stable at high temperatures. So, for instance, nanostructure of gold start to change shape and collapse around 300, 400 degrees C. So this means that the designer optical properties that we have created are being lost, and so we don't have any more the functionality in the device that we have created. And so here you can see, this article reports some example of different plasmonic materials, and as a function of the frequency of plasmonic resonances and also the carrier mobility. So we can see that depending, of course, on the frequency range of operation, we can select different materials, and these materials should be selected upon their physical properties and upon, of course, the final target application that we want to develop. And among these, the metal nitrides are very interesting because of optical properties in the visible, which are very similar to gold. But beside this, they, as you can see here, they have golden luster, so very similar to a gold film. And maybe you have seen these drill bits, which are coated by titanium nitride. And beside these optical properties, which are similar to golds in the similar wavelength range, so they are really refractory, so high melting point. They melt around 2,700 degrees C. They are really chemically stable in harsh environment, so in strong acid and basic, there is no change of composition. And they are biocompatible and also CMOS compatible, so they can be integrated in the technology of semiconductors, for instance. So that's why there has been really a great interest in the last 6 years about titanium nitride. And in my talk, I will start talking about plasma-enhanced catalysis in the first part. In the second part, I will switch to solar thermal technologies. So the first, one of the main research topics in my group is photoelectrochemical water splitting. So maybe I will just go through really quickly to what's happening in a photoelectrochemical cell. So usually, photoelectrochemical cell use semiconductor, which are in contact with an electrolyte. And we will have a wire which connects one electrode to the others, and that will bring current into the circuit. When we put the semiconductor in the electrolyte, there is a formation of the so-called depletion layer. So we have like band bending at the interface with the liquid. And so when we shine the light, we form electron holes which has very high energy, and that can be separated thanks to the formation of these depletion layers. So therefore, we can use these highly energetic carriers to drive chemical reactions. And of course, this is in this case, we are talking about water splitting, so which means we have water, and we can design materials which split the water into oxygen and hydrogen. This is not so easy, and indeed is like this. The first report about water splitting was in '72, and so far there is really no technology which is commercialized about this. And this is, of course, for many reasons. So as you can see here, so you see that in this, the mechanism of function basically is similar to a photoelectric effect, but in this case, so similar to what's going on in solar cells. But the only thing which is different is that we have the electrolyte and so the chemicals which are in contact with this semiconductor. And this has really changed everything because, for example, we cannot use silicon on 3-5 semiconductor, which has very nice, of course, performance for photovoltaics. But if you use silicon or 3-5 semiconductor here, we will have really the corrosion of the devices. And so the device will last for 10 hours at maximum. That's why there is a big interest in the use of metal oxide, which are quite also cheaper from a point of view of the processing, and they are much more stable, and they are very stable in photoelectrochemical conditions. So the only problem with this is that metal oxide, that titanium oxide, or bismuth vanadate, or hematite, which is rust, basically, they have very very high recombination of carriers. They have also very low absorption of light, usually, and also they have low carrier mobility. So how can we increase the efficiency of the device made by these materials? And one possibility is to use, of course, plasmonics, because we can concentrate light at the nanoscale and modify or perturb the generation of carriers inside the semiconductor. And we can do this in many different ways. For example, you can take a look at this review, which has been published recently. And we can do this in very different ways. So if we think to what's happening when we excite light to metal nanoparticles or metal nanostructures, so we have this oscillation of conducting electrodes, which has really a short time, lifetime, which on the order of 10 or 15 femtosecond. And so when we shine the light, we concentrate light close to the semiconductor. And for example, we can increase the efficiency of our device by using resonant excitation between the plasmon and the band gap of the semiconductor. So we can use the scattering coming from the particles in the plasmonic materials to enhance the rate of interband transition in the semiconductor. And so we, of course, achieve much higher current, so much higher efficiency in our devices. What we can do also, we can use the what happened after the dissipation of the surface plasma. So we can use the hot electron and hole pairs, which are generated inside the metal nanoparticles, and they can be injected in the semiconductor conduction band. So these carriers should have energy higher of the Schottky barrier which forms at the interface. And this is an interesting approach because in this way we can use energy, hot electrons which have energy which is lower than the gap of semiconductors. So let's say that we use titanium oxide which has a band gap of 3.2 eV or which absorb around up to 420 nanometers. So we can use also energy which comes from the spectral region of 500, 700, and 800 nanometers. So we can use different plasmonic materials, excited plasmon, and use the hot electron which decays from them. And so this means that we have a photo responsivity from the device, which not comes only from the region of the band gap, but also for using below band gap photons. So of course this can be an interesting way to enhance the activity of our materials. And so there is also other different way to do this. So there is a cascade of events. And finally, we can use also the heating coming from the surface plasma, for example, to modify the fundamental properties of charge transport inside the semiconductor itself. So about this, we start working with titanium nitride in 2015. And what we were interested to do is was to compare the potential of titanium nitride versus the gold particles, which is usually the benchmark material for this kind of study. And as we can see here from the cross-section of absorption, we can see that indeed titanium nitride presents really different properties with respect with gold. We can see that gold presents sharp resonances in the sharp resonance in the visible. Otherwise, for titanium nitride with similar particles, like this is nanocube, with the same dimension, we have much broader cross-section absorption, so we can cover much bigger wavelength range. And so, of course, we can absorb much more light and use it for our purpose, in this case, water splitting. So what we did, we developed titanium oxide nanowires electrodes, where we deposit gold particles or titanium nitride particles. And as you can see here, the absorption of the particle deposited on the top of the electrode increased the absorption at longer wavelength with respect to the band gap of titanium oxide. And then we measure, of course, the efficiency of our materials in a photoelectrochemical cell. Here is the JV curve of titanium oxide, pristine titanium oxide. And here there is the curve of the electrode where we deposit the same amount of gold or titanium nitride. And you can see that we got the doubling of the current from the pristine material to the titanium nitride, titanium oxide composite, but also that titanium nitride overperformed gold by 25%, which was really not bad. So we started to go a bit more deeper in this, and we measure, for example, the wavelength-dependent photocurrent and calculate the IPC, so the incident to photon current efficiency, which can give you the motivation why we have this increase or what kind of photons you are using. And so you can see, and you can see that here there is a spectral response of the photocurrent as a function of the wavelength. We can see that we have a current coming from the region where the surface plasma of titanium nitride is expressed, or otherwise the gold particles. But also we have contribution for interband transition in the metals. And what we did also was to try to understand what was happening at the interface between these two metals, because the interface where when you put a metal to a semiconductor, of course, can be the creation of potential barrier, and this potential barrier is fundamental to determine how much electrons go on the other side from the metal to the semiconductor. And therefore, we did some electrical measurement, and we saw indeed that in contrast to gold, where of course we saw the normal formation of a Schottky barrier between the metal and the semiconductor, we saw a kind of formation of ohmic junction between the titanium nitride and titanium oxide. Maybe there is not really ohmic junction. There is a small barrier, a small potential barrier, but of course, anyhow, is really very much smaller than what is formed in the titanium oxide. So of course, the barrier from one side is important because it helps to divide the charges, so to keep the charges on the semiconductor and the holes in the metals. But on the other side, when we are talking about photoelectrochemical device, we can a bit play with the bias that we apply into these diodes, and so the possibility to have lower barriers really helps to have much higher hot electrons, which goes from the metals to the semiconductor. And indeed, we did some calculation in collaboration with Sasha Govorov, and which calculate the amount of hot electrons going from the metals to the semiconductor. So here is the rate of high energy electrons, which really makes into the semiconductor, considering the experimental values of the barriers. And as we can see here, the rate of high energy electrons which goes on the other side into the semiconductor is much higher. So you can see that if you integrate this contribution of titanium nitride versus gold, we have like 2 times higher hot electrons which goes on the semiconductor. So then this doesn't really fit with the 25% increase that we saw in the photocurrent, but okay, this is a theory, and there are so many other different parameters to take into account to really estimate precisely how many electrons goes from the metals to the semiconductor. Anyhow, this of course now is a titanium nitride has also been used in other photoelectrochemical device. Recently, there's been reported also current much higher than what we reported, go up to 4 milliamps, and so this start to really be interesting for real devices that should have at least 10 milliamps per square centimeter to deploy some kind of device which can return the investment done for the development of the devices. So after this introduction into the use of hot electrons, now into semiconductor metal hybrids, I want just to switch to the use of pure hot electrons in metals and talk about the so-called plasmonic catalysis, which has been, let's say, introduced by the Lynch group at the University of Michigan around 2011, and then there was also really a big contribution from Halla's group in the years came later. And in particular, so in this case, we have just the plasmonic metal, so nothing else, and we excite the plasmon, and after decay of the plasmon, we have the formation of these hot electrons with very high energy that can interact with the molecules which absorb on the surface. And this all really has been demonstrated so far to be able to drive chemical heterogeneous catalysis with much lower energy. So and also change selectivity. So if you think to a chemical reaction, usually we have the reactants which start to interact with each other. There's the breaking of some bonds, the creation of other bonds, and so from an energetic point of view, the reaction goes through a specific surface potential energy which overcome a maximum, which usually is called the transition state of the reaction. Then we go down again with the energy to form the product after the formation of the products. And of course, what the chemical industry normally uses is thermal energy to drive more efficiently the chemical reactions. But by using hot electrons, so what we can do is we can do something similar to thermal energy. So we can activate the transition state of chemical reaction, and so decrease the energy necessary, for example, for produce hydrogen from styrene forming or other really important chemical reaction, or to produce polymers and so on and so forth. And so this has been demonstrated with just pure plasmonic metals, in this case silver, and thereafter, a few years later, has been introduced the concept of antenna reactors. So usually plasmonic metals are not very efficient catalysts, and therefore with this idea it's possible to combine the efficient concentration of light. So we use really an efficient antenna, like for example silver, and we put a small particle of catalytic materials just aside. For example, palladium, rhodium, platinum, all these material, 3D transition material are very good catalysts. And what's happening is that the let's say the lossy nature of the catalytic metals makes the surface plasma dissipate really on the surface of the metal, so we can create lots of hot electrons on the surface of the metals, and therefore drive efficiently catalysis. So also in all this demonstration has been usually performed with silver or gold or aluminum, which is also an alternative plasmonic materials which has been developed by Alas Group. So in our case, we started last year when I moved to Olomouc in the Czech Republic to study titanium nitride platinum antenna reactor system and to drive the hydrogen production from ammonium borane. So ammonium borane is quite important molecules, which was listed like among the 10th more important molecules for the US Department of Energy, because it has very large possibility to host hydrogen inside the structure. And so if we decompose ammonium borane, we can get 3 molecules of hydrogen per molecule of ammonium borane. And of course, this can be interesting. So what we studied right now, this is again in collaboration with Sasha Govorov, and we're just finishing the paper and writing the paper right now. So we studied the use of titanium nitride with platinum for this catalysis. As you can see from our simulation, it's interesting to compare the properties of, for example, silver and platinum hybrids. You can see that in the silver we have always quite a big amount of scattered light, which scatter back from the surface of this material. Otherwise, for titanium nitride, we have really a low amount of scattered light, and most of the light is absorbed inside the materials. This means that we can really really create a large amount of electrons or heat by using these hybrids. And here again is more clear. We can see that the excitation of the resonant excitation of surface plasma in titanium nitride cubes, where we just put 1 particles of platinum. As we can see that, of course, we have the hot spots of the surface plasma in the vertices of the titanium nitride, but also this plasma decay on the surface of our catalytic material, so which is what we want for this kind of reaction. Okay, this is our really nice materials, which my postdoc prepared, very nice. We put through a wet chemical method, we deposit many platinum nanocrystal, 3 nanometer average size on a 50 nanometer titanium nitride cube, and which of course show plasmonic resonance. Here you can see that we use free electrons to excite the surface plasma resonance, the dipolar surface plasma resonance through the use of EELs. And you can see really how much is the propagation of electric fields around the cubes of the titanium nitride, which also invests really all the platinum particles which are deposited on the surface of the catalyst. And so here, what we did, we studied with concentrated solar light, the hydrogen production from ammonium borane by using different light intensity. You can see that here is the dark temperature, so room temperature in the dark. So this is the activity of hydrogen production from ammonium borane with our catalyst in the dark. And then by shining the light, we can have like 10 times more higher activity of hydrogen production with our photocatalyst. The thing is that when you shine the light, really you can create significant temperature, and so this change also the dark chemical reaction rate. Indeed, if we measure the temperature when we shine the 1, 2, 3, up to 10 sun, we can create really, we can vary the temperature of the reactors from, let's say, 25 degrees to up to almost 50 degrees. So of course at 50 degrees the reaction would go much faster. And so what we did is a series of blank experiments at the so-called plasmonic temperature, but not shining the light. And so here is the contribution. Basically, with this method, we were able to distinguish between the contribution due to the thermal effect of plasmons and the hot electrons, which of course come if you subtract this contribution to this big contribution. So And so this is to say that at 10 sun, for example, the pure hot electrons activity for hydrogen generation is 2 times more than the thermal contribution which we have by using this hybrid catalyst. So here is just some mechanisms inside. You can see that if we do wavelength dependent, so the reaction at just using not solar light but one wavelength, we achieve like rate of hydrogen production which followed the surface plasma resonance. So this is kind of signature of the nature of our reaction. And also we can see that we observe a change of electron regime by using different light intensity. So we have a change by linear dependence of the rate of hydrogen generation to a supralinear dependence. In this case, this has been reported to be due to the switch from a regime where just one electron is excited and it is used in the reaction to a regime where we have multi-electrons which participate to the reaction. And this, of course, is really the gain of plasma. So we if we think the difference with semiconductor, for example, so with semiconductor in photocatalysis, we excite one photon, usually one electrons on one holes, and so we have like one type of interaction. With plasma, so one photons really excite many electrons, which of course forms the plasmons, and therefore the formation of hot electrons results maybe in many, results of course in many hot electrons per photons. And indeed we have results which show that in this reaction we have like more than one, I don't know, we have preliminary results that show that we have more than 100% quantum yield in the reaction, which is like the double of what has been reported for silver. And of course this can come from the much more efficient absorption of the light in titanium nitride, but also the difference in, for example, carrier density inside the materials. And this of course is important because electron scattering, so energy dissipation of hot electrons can be limited if you have less carriers inside the materials. And so finally, this is just the picture of what I was saying before. So this is a normal thermal reaction, and this is a catalyzed reaction, or what we have here. So we decrease the activation energy barrier of the reaction by using hot electrons, and specifically by using an Arrhenius equation, we see that we can decrease by 20 kilojoule per mole the energy due to needed to drive the reaction, if we compare, of course, the photochemical to the thermal reaction itself. And so this is just a picture of the mechanism. Basically, we have, okay, I will just skip. Basically, with the production of hot electrons, we provide much more electron density on the surface, and this accelerates the breaking of the OH bond, and so we have more hydrogen, atom hydrogen, that can participate in the formation of hydrogen molecules into the reactions. So now I just want to switch to the use of plasmonic nitride in the regime of high temperatures. And I want to introduce this section by, so of course this is just what I was saying before. We have what's happening in the plasmon. So we have the excitation of the plasmons, the formation of hot carriers. So we have the formation of a Fermi-Dirac distribution with hot energy distribution of electron and holes. And then after picosecond, we have the heating of the lattice of the materials. And so we can really use this heating for doing many things. And so what we have to consider, this heating comes for Joule effect. And so what we have to consider to understand how much heat we produce in the material is the electric field inside the materials and the optical losses, so the imaginary part of the permittivity of our materials. And here it's interesting, a series of interesting studies has been published like in the last 3 years. where optical properties of different materials have been studied in temperature. And here you can really see that if you calculate analytically the figure of merit of silver, gold versus titanium nitride, you can really see that above 400 degrees C, the figure of merit becomes equal. So the refractory materials have the same quality of the optical properties of the noble metals, which of course really is a strong motivation to use these refractory materials for high temperature application or an harsh environment above, for example, 400 degrees C. And this is a really astonishing example which was developed in the Shalive group in the Purdue. They develop a metamaterial absorber and emitter for solar thermal photovoltaics, and they try to really heat up the temperature up to 800 degrees C, or use a high energy amount of energy by pulsed laser. And you can see that the titanium nitride really doesn't change anything in shape and organization of the metastructure. Otherwise, gold really collapsed and we lost some pieces. The shape is changed. And so this really demonstrates the outstanding performance of these materials for the high temperature, extreme temperature regimes. And from this, so this was the motivation for my work that I'm going to show you. Of course, these nice metamaterials, nice properties, the nice arrangements of nanostructure are usually produced by beam lithography, or a method which allows to produce microscale patterns. So this is really not really convenient if you want to produce solar thermal technology on a massive scale, on a square meter scale. And therefore, what we think was to use to start from titanium oxide nanostructure and nitridize this structure to titanium nitride. So basically, we put the metal foil inside an electrolyte, a titanium metal foil, and through corrosion, so basically, we create self-assembled nanocavities, which creates hexagonal lattice into the materials, and these are created like centimeter long, very regularly along our metals, our foils. Here you can see cross-section and also high resolution TM mapping of a lamella of our materials. You can see that we create, this is titanium oxide, this is titanium nitride after nitridation, so we create really small cavities of 80 nanometer in aperture and 150 to 200 nanometer in length. And as you can see, these are really very small nanostructure that, of course, can sustain surface plasmons. And here is the absorption of our materials. You can see that they really provide exceptional properties of absorption in the visible and near infrared. We can, the experimental curve of pure titanium nitride is the solid red curve. We can absorb 95% of light at 470 nanometer, or 97% if you count either the range between 300 and 1100 nanometers. Of course, if you modify the structure with alumina, for example, we can modify the interaction with light, and we can reach like this 97% of light, even if we extend the range up to 2200 nanometer of the range. And what's happening here is similar to what's happening in the cavity, in the photonic crystal cavity. Basically, we have light which couples with this sub-wavelength cavity, so there is a formation of fundamental cavity modes inside this nanostructure, which also hybridize with surface plasmon polaritons in the walls of the nanostructure. And the lossy nature of the titanium nitride and also the roughness of these materials really produce a very high absorption in the visible and near infrared. And so after really create this unique structure, we start thinking also how we can tune the absorption. Here, maybe I can skip this. But fundamental and interesting properties of these materials is that they are done by very small crystals of around 5 nanometers, which which is quite unusual for plasmonic materials. Usually use single crystal or e-beam lithography made materials, which has like 40 or 50 nanometers of crystal size. So when you have such small crystal, basically the dissipation or the electron relaxation rate can be really influenced by the electron scattering at grain boundaries. And so what we did, we used just the very simple models, Mayada's models, which connects the size of our crystals with electron relaxation rate or the electron relaxation time. As we can see here, by using this simple expression, we can calculate how much is the electron relaxation rate for the plasmons inside our materials. And we can see that we achieve for the smallest crystal size that we obtain really, really high electron relaxation rate if you compare, for example, with silver or gold, which usually has been reported to be 50 or 100 milli electron volts. So this, of course, means that the quality of our plasma is not very, very high, but also that we have really big dissipation inside the materials that can be used to produce heat, for instance. And so we use these materials to produce solar heating. And as we can see, our materials really outperform reference materials such as titanium foil or titanium oxide cavities. And remarkably, we can achieve with very moderate concentrated solar power, like temperature above 600 degrees C. And this is quite interesting because, for example, solar thermal technology like solar towers reach this temperature by using two order of magnitude higher concentrated solar power. So, which means that we can use really surface plasma to develop a new generation of solar thermal technology to concentrate light and do something of useful. Of course, I can skip this. In air, the titanium nitride is not stable, but if you use argon or vacuum, our material is stable. And I just want to go to the application. So what we did is to shine the light with 15 sun to our materials, which was prior basically immersed in a solution of iron acetylacetoate. And so after illumination, basically, of 4 hours in vacuum, we see that the disordered deposit transforming conformal coating. You can see here a nice conformal coating of iron oxide on the mouth of these cavities and all along the structures. And by Raman, we saw that this is hematite, so iron oxide again. But really, so we can obtain conformal deposition of materials just using the local heating in the walls of the material, so where the electric field is concentrated. And what we see also that this temperature catalyzes the formation of new carbon bonds. So this tells us, basically explains also the motivation of these materials is not only to measure high temperature, but of course what we're now doing is to use this to drive process like methane reforming or hydrogen production and CO2 reduction by using just the solar light and heat generation with plasmons. And finally, very briefly, sorry, but this probably is interesting for you, is the steam generation or water purification by using heat produced by plasmonic materials. Maybe this was mentioned yesterday. This is the same, of course, principle using photothermal therapy. So we shine the light on the metal particles, we produce heat, and we can use this for something. In this case, for example, also Halas reported in 2013 the possibility to generate steam or to purify water by using metal nanoparticles inside some reactor. So here we can see that this field really exploded like in the last 3 years, and many different methods have been used, from nanoparticles to nanoparticle, for example, deposited inside membranes of alumina. Here they show, for example, that we can use floating membrane, where inside we have plasmonic particles, and we can desalinate water in a very efficient way. So this, of course, is very interesting for many different countries which has problem with water or with fresh water. And so this, what we did, this is just preliminary. We use our nano furnace to evaporate water with concentrated sunlight. These are the reference value in the literature. The best materials can produce 14 kilogram per square meter per hour of water, basically. Of course, that can be collected by normal condensation of the vapors. And so we try and give a try with our materials, and we achieve basically 26.5 kilograms per square meter per hour by using a damaged sample. So this is very promising. It means that I'm confident that we can reach 40 kilograms per square meter per hour just by using 10 sun, which, for example, can be just achieved by using a plastic Fresnel lens, which costs $10, for example. And so this is just to conclude. Again, I think this is what I want to show today is the possibility to use really different materials for plasmonics, and that plasmonics can be used not only for communication, but also for solar renewable energy. And for this field, we can develop many different things, from a catalyst for hydrogen production to solar thermal devices which can drive chemical reaction in an efficient way, or purify water, for example, to produce fresh water for developing country. So with this, I would just want to conclude and thank you all my group into Czech Republic, my collaborators are Purdue and Sasha Govard, and of course all of you for the kind attention. Thank you.
Thank you, Alberto, for this very nice talk. So we have time for some questions.
Hello, everyone. Excuse me. I'm going to practice my English. Well, I like to ask you about what about the chemical reactivity of the material? I'd like to know. I would like to know how this material behaves when it is surrounded by oxygen atmosphere, for example. What about this? What about the reaction with, for example, another kind of acids or chemical agents, like, you know, well,
Yes.
that kind of things.
Yes. I think.
Thank you.
Thanks. Thanks for the question. So one of the strong points for metal nitrides is really that they resist to harsh environment like strong acid, and so it's very convenient to use these, for example, in solution where you have strong condition like strong basic or acid. If you want to, of course, there is a problem if you want to use these materials in a gas phase reaction, which contains oxygen, because in this condition, titanium nitride goes back to titanium oxide, so it's not anymore plasmonics. So you maybe can cover the titanium nitride crystal with some protective shells or do something like this. But I think it's more promising for a solution or liquid phase reaction.
So in this case, in the kind of application that I need to take, we have to take in mind that kind of things. For example, about into oxygen exposition and that kind of thing.
Definitely. This is very important. This is very crucial.
Okay. Any other question? Molly?
But first, excuse me.
About this is steam generation, what's the actual mechanism? Because if I understood well, water is not boiling. So what's the mechanism that you generate the water vapor?
Well, this is for the bulk. I really don't know yet. I mean, for the here for the interfacial, let's say evaporation. So when if you use like this kind of configuration, let's say, I think you create really some special condition here in the liquids. I don't know, superheated of the liquids, and I don't know, you create really enhanced evaporation. And for the bulk heating, there's you see bubbles which are generated actually. So you really eats up all the bulk liquid, but you don't have like the boiling like when you cook pasta, for instance. So I don't know the exact physical mechanism, like microscopically speaking about what is going on, like what's the condition of the gas dissolved inside the liquids, or so for this we have to go through much deeper probably what we're doing right now.
Okay, thank you.
Can we find those benefits of titanium nitride just from looking at his crystalline structure?
So, sorry, can you repeat, please?
Just take a look at the crystalline structure of the titanium nitride. Can we find those benefits just from looking at it?
What benefits? The stability or
Whatever.
in general? No. No, I think no. So you have to study the optical properties of the materials if you want to compare with other metals or other materials, and see, what is your permittivity, so the metallicity of your materials, the optical losses, and so on and so forth. And then so you can decide you can design your device, of course, doing simulations and so on.
So crystalline structure doesn't give us a lot of information.
Well, the crystalline structure give you, if it's titanium nitride, if it's cubic titanium nitride, very well, nice. If it's you can understand if it's stoichiometric or not, maybe from that. And this is also important because another interesting point of titanium nitride is that you can have different stoichiometry, and all these under stoichiometric titanium nitride and also stoichiometric titanium nitride are plasmonic materials. So you can have different class of plasmonic materials itself. And of course they can behave differently, like they can have different optical properties as well. Because you change the carrier density, you change.
Okay, thank you. Any other questions from here? And then
thinking about the things that you were saying about complete energy, like you generate energy and then you have to, the waste of that energy usually is heat, right?
Yes.
So can you couple like antennas with this generator of heat?
Actually, we use antenna to generate heat. It's like this is kind of, the plasmonic materials historically started to be used in nano optics, and so used for communication and so on. But the problem with that is that they have very high losses, and also they are not compatible with normal semiconductor industry. So people start to look at different materials like dielectrics and so on. And on the other side, people working with the plasmonic materials start to look at to the losses of the material. So basically they transform the losses into gain and try to think how to use these losses for different applications. So this is just, again, an antenna, plasmonic antenna, but we don't care anymore about the quality of the resonance, but we care more about what's happened after the dissipation of the plasmons.
okay, thank you. There are a few questions more, but okay, last question, because we have to finish. Professor Rafael.
Thank you. Generally, it's more easy to have polycrystalline samples than monocrystalline samples. For example, for the titanium nitride, which is the rule? Which is the rule of the size of the grain in your results?
Well, yeah, we should. So with a single crystal, you can really have nice quality resonances. While with this, if you have polycrystalline, as you show here, basically we have really lots of dissipation of and very high electron dissipation rate, relaxation rate, because these more crystallines. So these more crystalline are very much lower than the electron mean through path of the electrons, and so you have really lots of scattering events of your electron, which forms your surface plasmon, and so you can basically accelerate, if I can say that, the dissipation and the formation of heat or hot electrons.
Okay, let's thank the speaker again.